we've got our concentration terms, we've got our flow rates. Do we have everything that we need to solve the problem? If not, what are we missing? Energy balance, right. We got to get K's, and they're not constant if the temperature is not constant. So that's why we need the energy balance. So let's look at what the energy balance looks like for this problem. dTdV I'm going to put this form up here just to remind you a little bit about where it came from. So some amount of heat generated, some amount of heat removed divided by a resistance, which is related to the flow rate and heat capacity. More flow means less temperature change, right? That kind of makes sense. Greater the heat capacity, less temperature change.
Is that Fi or Fj?
Should be J, whatever my I. Man, I am terrible about that. I love flipping those. All right, what is Q removed? No, not this case. No sum. This is removed. Removed from the system. No delta H. Delta H is what we call generated. UA, and then because it's removed, it's T minus TA. And then QG is the sum over the reactions, negative Rij times negative delta H reaction at the temperature, but for this problem, we know that the delta H reactions don't change. Why not? Because delta CPs are all 0. And so it's just the one that was given, and again, Ij. So that's our heat generated term. Yeah.
In regards to our counting things here, that's I think the I's and J's get switched because I don't think that it's consistent.
Yeah, it's not
in
consistent.
the book. So like, but the bottom denominator on the dTdV is for each flow rate of species.
Yes, this is each species, this is each reaction.
Yeah.
I think what makes more sense is to make this one J. Because this becomes species over here. Because that's why we write R1A.
But right.
Yeah. So if you want your notes to be fully consistent, you would make these
Okay.
J's. All right, so putting it all together, you get dTdV, the UA TA minus T. Notice that this is flipped from T minus TA to TA minus T. That's because up here it's negative QR. Plus, how many reactions do we have? 2. So the first thing we put here is negative R1A. Not RA, not R1, R1A. Negative delta H reaction, 1A, plus negative R2A, negative delta H reaction, 2A. And then this whole thing is just divided by the flow rate of each species times the constant temperature heat capacity of that species. So FA, CPA, FB, CPB, plus FC, CPC. Okay, any questions? I think the one thing that you got to be careful with is that this is not the consumption of A or anything like that. It's that R1A term that we defined earlier, and then the R2A term. Okay. So I'm going to start by setting this up, and then at some point I'm just going to open the one that I've already made to save some time. But I know it's kind of silly for me to just go, it's kind of like that draw an owl comic or whatever, where it's like draw a circle and then a second later it's like, it looks like an owl. I don't want to just jump straight to the finished product. Yeah?
Are you putting all those delta H reaction terms only in terms of the reactions? Is that how you're picking it? It's like
You're given per mole A.
Right.
So that's why you need to know that it's got to be, that you got to multiply it by the reaction of 1A.
Okay.
Does that make sense?
Yeah.
Not reaction 1, not reaction 2, but the rate of 1 in terms of A.
So rate is whatever the delta H reaction is in terms of.
Yeah, and the same, similarly to the K's, right? You're given K1A and K2A, so that's what you use.
Right.
Of course, if you're given what you don't need, you can always convert them with the stoichiometric coefficient. Okay, so where do we start? Volume, right? Oh, what am I doing? You guys can't see this. Okay, so upper left, volume, right? Again, that's what we're going to be dragging down, and that's what we're going to be, doing our delta V. That's how we're numerically solving our differential equations. That's our independent variable now is volume. Sometimes it can be time, sometimes it can be residence time, like for CSTR here, it's just volume. So now what else can we put? We can put the concentration of A, B, C. We can put the rate of each. So these are the net rates of formation and production of each. How do I know which things to put? Well, remember that the differential equations are all written in terms of RA, RB, RC. So it kind of makes sense to put those in here. The concentrations can vary, so it's just a little bit helpful to put them as columns. You don't have to, but it saves you some time because you're going to have to put concentration of A inside the rate of A, the rate of B, the rate of C. So it just saves you a little bit of time in terms of putting in the formulas.
And this is 1A, 1B. Or is this?
No, this is just the net rate.
Okay, net. Okay, gotcha.
Because again, that's where our material balance is written, right? It was DFA dV is equal to RA, not 1A. You're right, though, that if you want, you can put 1A, and that can be useful for the energy balance. But I didn't do that in my other one, so I'm not going to do it in this one. FA, FB, FC, right? The flow rates of your species. That you're going to have because it literally asks you to show the flow rate profiles with the volume. Temperature, of course. And then again, in terms of being helpful, you can put K1A and K2A because those are going to change with temperature. And so rather than embedding the formula every time you need it, it's just nice to have it as its own column. So again, the only ones that you absolutely have to have are volume and flow rate and temperature. But all these others make my life easier, so I'm including them. Plus, it means that we're able to, if we want to, show a plot of that variable over the size of the reaction. All right, and then over here we've got sort of stuff that we're given, right? So we're given a lot of information. Here's where I'm going to cheat a little bit. No, we'll put it in. Ca naught, 0.1 moles per liter. Fa naught is 100 moles per second. BH reaction 1, negative 20,000 joules per mole.
Mole A, right?
Say that again?
Mole A.
Yeah, I mean you could have wrote that in there, but it's not a big deal. Heat capacity 90, heat capacity B 90, heat capacity of C 80 joules per mole. UA 4,000 joules per liter second Kelvin. TA 373, T naught, 423, those are both in Kelvin. And then EA 1 over R, 4,000 Kelvin, EA 2 over R, 9,000 Kelvin. I think that's it. Can anybody remember anything else that's given? All right, so what's the initial volume? 0, right? And then we have some delta V that we're going to use to increment volume. And I know, because I've already done this problem, what to put here. But if not, you can just change it. I mean, it doesn't. You don't have to know it. You don't have to get it right the first time. But this is a fairly small reactor. All right, what's the initial concentration of A? Ca naught. What's the initial concentration of B? 0. C? 0. We're going to skip these for the time being. What's the initial flow rate of A? Fa naught. What's the initial flow rate of B? What's the initial temperature? T naught. And what's the, we can go ahead and put these in. Our formula for our rate equation is 10 times the exponent of EA1 over R times 1 over 300 minus 1 over the temperature. So the initial one there is this, 420, 483. I'm going to do my thing where I make it so that the cell references don't change. And this one, the only difference is this is 9,000, and instead of 10, the value is 0.09. But it was also at 300.
F3 or F4? Yeah, I tried to do it on Mac, but it didn't work.
Yeah, F4 is what it is on Windows. Did somebody have another comment? Yeah.
It's 1 over 5 something instead of 1 over 300.
And that was the problem before this one, I believe. No, thanks. I mean, I'm fairly certain. It's not going to make a big difference, but I think it was a problem before. I might have wrote it wrong on the board.